This video is going to explain about Krebs cycle. The learning outcome is for students to be able to illustrate to explain Krebs cycle. What is Krebs cycle? It is a chemical reaction, a series of chemical reactions in aerobic respiration. So it starts with acetyl coenzyme A that will be completely degraded to carbon dioxide and water with the release of metabolic energy that is used to produce ATP. So in summary, it is an aerobic respiration. Involve acetyl coenzyme A. Then acetyl coenzyme A will be degraded to carbon dioxide and water. And this process produces ATP. Krebs cycle is also known as tricarboxylic acid cycle or citric acid cycle. The name Krebs comes from the founder of this Krebs cycle, which is Mr. Hans Krebs. Krebs cycle is the second stage in aerobic respiration. Occurs in the matrix of mitochondria. You should mention matrix of mitochondria. You cannot just mention occurs in the mitochondria. Looking at this diagram, it shows that first stage is the glycolysis, which yield two pyruvates. Then pyruvate is transported into the mitochondria, which will undergo link reaction to convert pyruvate into acetyl coenzyme A. So this molecule will enter Krebs cycle for the second stage of aerobic respiration. Let's look at the products of Krebs cycle. As a whole, the yield of Krebs cycle should have ATP and ADH, FADH2, and carbon dioxide. So this amount involves 2 turns of Krebs cycle. Why 2 turns? Because we have 2 acetyl-CoA. Okay, where does acetyl-CoA comes from? From 2 pyruvate. So please remember that. And the pyruvate, of course, come from the glycolysis. So if the question asks from 1 molecule of pyruvate, then we should divide by 2. It's only 1 ATP, 3 NADH, 1 FADH2, and 2 carbon dioxide. This is a diagram that shows there are 8 steps in Krebs cycle. Starts with the binding of acetyl-CoA to its molecule, oxaloacetate. And then it is named as cycle because in the beginning oxaloacetate will bind to the acetyl-CoA, and then the cycle will yield another oxaloacetate. So it starts again with the same sub-processes. Step 1. When acetyl-CoA bind to the coenzyme A, the bond is not stable. It's an unstable bond, so it can easily break. So the breaking of the coenzyme A from the acetyl-CoA will give chance or energy for oxaloacetate or for acetyl-CoA to bind with the oxaloacetate. So acetyl-CoA is a 2 carbon molecule, oxaloacetate is 4 carbon molecule. So this binding of the 2 carbon molecule and 4 carbon molecule will yield citrate, a 6 carbon molecule. So the coenzyme A will be free to combine with any other molecules in the matrix of mitochondria, either in the link reaction or in the next steps of Krebs cycle. Step 2 is isomerization. Involves citrate, isomerize to its isomer, isocitrate. Citrate is 6 carbon molecule. Isocitrate is also 6 carbon molecule. This process is isomerization. It does not involve any change in the molecular formula. Step 3 involves oxidation and decarboxylation. So since this occurs in the presence of oxygen, is also termed of as oxidative decarboxylation, and it also involves the redox reaction. Okay, let's look at where the redox reaction is involved. First, isocitrate is oxidized. So this is the oxidation, which means it releases the hydrogen atom. The ion, two hydrogen molecules involve electron and hydrogen ion. So since isocitrate is oxidized, the oxidizing agent is the NAD+. So in this process, NAD+ is reduced to NADH. And after oxidation, decarboxylation occurs, which releases a carboxyl group from the isocitrate in the form of carbon dioxide. So isocitrate is 6 carbon molecules. Since it's lost 1 carbon, alpha ketoglutarate of course is a 5 carbon molecule. Okay. In step 3, remember in step 3, carbon dioxide is released and NADH is formed, and then isocitrate is oxidized to alpha ketoglutarate, oxidized and decarboxylated. Step 4 involves decarboxylation first and then oxidation. So alpha ketoglutarate will release a carbon molecule from its molecule in the form of carbon dioxide. So it releases carbon dioxide, undergo decarboxylation. So just use the word decarboxylation. Alpha ketoglutarate undergoes decarboxylation. Carbon dioxide is released. Then it will be oxidized by releasing hydrogen to the NAD+. So NAD+ is reduced to NADH. Okay, next, this is an important step. Coenzyme A will be bound to the resulting molecules of 4 carbon, resulting molecule forming Succinyl-CoA. The bonding of coenzyme A to the Succinyl-CoA is not a stable bond, so it can be easily lost. The Succinyl-CoA in the next step is substrate level phosphorylation. So we know substrate level phosphorylation will yield ATP. Succinyl-CoA will lose the coenzyme A. So the release of coenzyme A will release energy. The bond breaking release energy. So the energy will be used to bind phosphate inorganic, that is in the matrix of mitochondria, inorganic phosphate inorganic to the GDP. Remember, the release of coenzyme A release energy. The energy is used to bind the phosphate inorganic to the GDP. So GDP then transform into GTP. Next, GTP will transfer the phosphate to the ADP, hence forming ATP. So this is what we call as substrate level phosphorylation that produce ATP. So walaupun perjalanan dia macam panjang, but in the end it produce ATP. Okay, we can say that Krebs cycle yield ATP. In step 5, Succinyl-CoA is converted to succinate. ATP is formed. So next, in step 6, oxidation process involved. Succinate is oxidized to fumarate. So let's look at the number of carbon. Succinyl-CoA is already 4 carbon. Succinate is 4 carbon. Succinate is oxidized to fumarate. Fumarate is also 4 carbon. So there will be no more decarboxylation or release of carbon dioxide. So succinate oxidized by transferring the hydrogen atom to the FADH2. Electron NH+. So FAD is reduced to FADH2, succinate is oxidized to fumarate. Next step is addition of water, step 7. The fumarate is rearranged to malate with the help of addition of water. Step 8. Step 8 is the last step. Involve oxidation and regeneration of oxaloacetate. So the malate for carbon molecule is oxidized to oxaloacetate. Here in this step, the oxidizing agent is the NAD+. NAD+ receive 2 hydrogen atoms to be reduced to NADH. So oxaloacetate will be ready to combine with another acetyl-CoA to start new cycle, Krebs cycle. So 1 turn, each turn of Krebs cycle, each turn, 1 turn, itu sama maksud dia involve 1 molecule of pyruvate, so we will have 1 ATP tadi, 2 carbon dioxide, 1 FADH2 dan 3 NADH. Okay. If we are discussing about 1 molecule of glucose, means that we have 2 turns of Krebs cycle because we have 2 pyruvates. Remember the difference. The difference is in the number based on the terms of the situation. So products from 2 pyruvate means 1 glucose. Okay, 1 glucose. Tapi 1 glucose dia akan involve glycolysis. Jadi kita nak start dekat dalam apa yang berlaku dalam mitochondria. Jadi 2 pyruvates lah sebab dah selepas glycolysis. So 2 pyruvates involve link reaction and Krebs cycle. Jadi molecule products, the net products should have 2 NADH, 2 carbon dioxide and 2 acetyl-CoA. And then kita akan tambah NADH ni ada juga terhasil dalam Krebs cycle. So we should have 8 NADH because Krebs cycle yields 6. Then we have 2 ATPs. We have 2 FADH which did not produce in the link reaction. And then another molecule carbon dioxide 4 plus 2, then we have 6 carbon dioxide. The total ATP produced by substrate level phosphorylation in the mitochondria, it does not involve glycolysis. It involves Krebs cycle. So the substrate level in the mitochondria produce only 2 ATPs. The link reaction and the Krebs cycle produce large quantities of electron carriers. The NADH and FADH2. So this molecule will move from the Krebs cycle and link reaction to the ETC, electron transport chain. Here, ETC, electron transport chain, and chemiosmosis, oxidative phosphorylation. So to memorize the substrates in the TCA cycle or the Krebs cycle, can I keep some succinate for myself? Oxaloacetate, citrate, isocitrate, ketoglutarate, Succinyl-CoA, succinate, fumarate, and malate. Or you can form your own mnemonic. Name the molecules that conserve most of the energy from the redox reactions of the Krebs cycle. Conserve maksudnya simpan. Okay, so who knows the answer? The answer is NADH and FADH2. How the energy converted to a form that can be used to make ATP? It conserves most of the energy. So how does the energy is converted to ATP? Through ETC and chemiosmosis. By NADH and FADH will donate the electrons because they are the electron carriers. So they will donate electrons to the ETC. Then we will learn later on how come ETC and chemiosmosis produce large amount of energy. Thank you.